All right, let's get started. Okay, so in our last lecture, so the homework was due already, right? So I will upload homework 2 as soon as possible. Yeah, and it'll be similar to homework 1, so we just have a bunch of textbook problems. Okay, so any question for homework 1? Do you feel okay? Yeah, so yeah, in the future, some of the homework will be really challenging. Yeah, so yeah, the textbook problems some of them are pretty hard. Okay, so who thinks the homework is okay? Yeah, who think it's hard? Huh? Same group of people. Yeah, okay, Miss Median. Yeah, so yeah, some of the problems are pretty challenging. So yeah, that's totally normal. Okay, so who solved all the problem without looking at the solution? Nobody? Okay, who can solve most of it without looking at the solution? Oh, really? Okay. Yeah, okay. Who didn't solve any of the problems but look at the solution? Okay, great. Yeah, that's okay. In my time, so there's no any solution for the textbook problem, and even the professor do not have the solution, right? Normally what we do is that the TA, well, there will be TA before, so the TA will solve all the problems, and then the solution will be the solution, right? So sometimes, I think there's a ones that, I think in my case, so that is probably 2010 or 2011. So at that time, so I think there's a one problem that nobody have the same solution. So we have in total I have like 12 students, including TA. So we have 12 answers. Yeah, and yeah, so that happens. So, but don't trust the solution too much, right? So, yeah, I made all solutions. So it is possible that I made some mistake. So if you look at the lecture video before, yeah, I didn't upload all of them yet, but for my old lecture video, there are lots of small mistakes. Yeah, not horrible, but there's small ones. Okay, yeah. Anyway, yeah, let's see what we covered in our last lecture. So in our last lecture, we finished talking about the chapter 4, so which is AEP for stationary ergodic process, and then we went back to our chapter 5 again, and then we'll focus on zero error code, right? So we'll give the introduction with all the definitions, and then we'll talk about the fixed to variable length code. Okay? Yeah, and so this is AEP for stationary ergodic process, and the first thing is that we need to be sure that what is ergodic here, right? And the ergodicity here we mean is called mean ergodic. So basically, we consider a stationary process, right? And then the time average equals to the ensemble average equals to expectation, right? And then it's called mean ergodic, right? And if you have, so we have some other kind of variance ergodic or whatever other ergodic as well, right? But here we only focus on the mean ergodic. Okay, and then if our process is stationary and ergodic, then we have this definition for our entropy typical set, right? And so this is pretty much the same as before, right? The only difference here is that here we replace the entropy by the entropy rate, right? So basically, in practice, although mostly we work on the IID case, right? But if we do not work on IID case, right, we do small extensions, right? What are the small extensions? It's ergodic stationary, right? It's not IID, but sort of like. Okay, and all right, and so this is our typical set, right, which is the same as before, and then yeah, we just said that, right? We just replace the entropy by the entropy rate. Okay, and okay, and for the lossless source code. Oh, so by the way, all the coding approach introduced for the IID or DMS source will work here. Okay, and for the lossless source code, here we care about the zero error code. Okay, so before we care about the epsilon error code, but now we just care about the zero error code. So that's very, very important. Okay, and the definition are as follows. We have a source alphabet denoted as this guy, right? And then, so we consider n of them together, right? Because we consider kind of like block code. Okay, and then we have this kind of definition. So basically, we consider the union with all kinds of the lengths of the source symbol, right, together. So as a union of the source alphabet, right? So here, so if we use X star here, so it includes everything, right? Could be block code, could be sequential code, and so on, right? And we use L to denote our code length, okay? And Y is all the possible lengths of all the possible lengths as well here, right, for Y. And later on, so we focus on the fixed to variable length code, right? So here instead of X star here, we use XN, right, to denote the fixed to variable length code. Okay, and here we have 4 possibilities, right? Fixed to variable length code, variable to fixed length code, variable to variable length code, and sequential code. Okay, and we don't have fixed to fixed length code, right? Because it doesn't make any sense, right? The key part here is that one thing can be variable. That's how we say, right? So we want to give more popular code, more popular source symbols, a shorter length, right? A less popular source symbol with a longer length. Okay, so that's basically the idea. So we focus on the so-called non-singular or non-singular code. So for non-singular code, it requires that if the source symbols are different, then the code word will be different. Okay. Yeah, so this is non-singular, and today we're going to use this concept here, right? So be careful here. For non-singular, it does not guarantee the decodability or the uniquely decodability, right? So because some symbol can be a prefix of others and so on, right? And sometimes it cannot be decoded if some symbols is a prefix of other symbols. All right, so, and then here is the definition of the fixed to variable length code. The definition is almost the same as before. The only difference here is that now we have xn instead of x star here, right? The lengths of the source symbol are always the same, okay? And then we have a decoding function here, and here we define, so g is the decoding function, f is the encoding function, so therefore the g of fx would equals to x, right? So we'll consider without any error, the case without any error, right? So it has to be absolutely equal to x for all x, okay? And we call this source code as NFG code. N is the length of the source symbol, F is the encoding function, and G is the decoding function, right? And we use this calligraphic C as the source code. All right, and with that said, so we can define code length. So basically that's the number of symbols in fx, right? And then the average code length is given by this function, right? So it's the expectation of the code length, right? Expectation is over all the source symbols, okay? So those would be our definition. And given that, we can have an upper bound for L, right? So basically it means that, so L can be upper bounded by the entropy plus some very small number that goes to 0, when n goes to infinity, okay? And we, of course, we consider DMS source here. Remember, DMS means IID, okay? All the symbols are IID. How to prove that, right? So basically it's a achievability result, right? So if you see anything like, so given an upper bound means that it's an achievability, right? If we want to see a lower bound, that means a converse, right? So this is the upper bound, so this is achievability, okay? And the key idea here is to use the variable length code, right? So basically the variable length, we only use 2 lengths, okay? One length to code the typical set, and the other length to code the atypical set, okay? And then by some manipulation, we can get this formula really easily. Okay, so that's what we finished in our last lecture. Okay, today we're going to continue talking about this. Today is our lecture number 18. So today, we're going to continue talking about fixed to variable length code. In particular, we're going to talk about uniquely decodable and prefix code. Okay. So I think it's rather obvious that why we need the code to be uniquely decodable, right? So if it's not, then we don't know what is the source information, right? So we need the code to be uniquely decodable. And then we'll talk about the prefix code. And the second topic is that, we need to see, okay, so let's say if we know what is uniquely decodable code, and then we want to construct it, right? And we want to see how to optimally, so what are the requirements to construct good code, okay? So second topic is called craft inequality. Right, so that will give you the condition that we can construct a good prefix code, okay? And after that, if we still have time, so we're going to talk about optimal code. Okay. Okay, so that'll be the idea for today. So let's see how much we can cover. Okay, first, uniquely decodable code. Okay, so we kind of talked about this before, so so for the slides, from the definition here, yeah, we can see that. So basically here we consider, for the source symbols, we consider the union of all possible lengths, right? But here we consider only length, one length, right? But now we're going to introduce a concept, it's called extension code, right? Extension code is nothing but, so we're going to concatenate a number of these n groups of source symbols all together and encode them all together. Okay, so let's see what is the definition here. So first we need to talk about what is the case extension code. So the case extension code of a NFG lossless source code is obtained by concatenating k blocks of length n of source symbols. Okay, so we concatenate k blocks of source symbols, and the block length for each one, the length is n, right? Which is the same as before. Okay. All right, and then the next is that we're going to encode them separately, right? It's not to encode them all together, so we encode them separately. So encoding them separately and forming extension code word as the concatenation of the original code word. Okay, so mathematically, basically is that the case extension encoding function is given by, we denote this by fk, okay? And then, so that is from xnk, right? Before we have the block length is n, so now we're going to do k of them all together, right? And then, so the output is the same as before, right? The encoded code word is the same as before, so that's y star. So, and such that, so this guy of x1, x2, xk, and each of them have length n, right? So that equals to encode them separately, right? So before our encoding function is f, right? So now we have fx1, and then so fx2, fx3, and so on until fxk, right? We just concatenate them all together, okay? So any questions so far? I just encode them separately and then put them together. So this is the case order or the case extension code, okay? And if we consider all of them, So then we have our star extension. Okay, star extension code C star of a NFG. Star extension of NFG. So it's called C star. So this is the union of all of them. It's a collection of all K extension codes for all K. Okay, so basically C star, so that's from X star to Y star, right? But it's different from the most general definition here, right? Still consider block code, right? It's just union of the K extension code for all the K. Okay, so that's the definition of the extension code. So we're going to use that later, right? If we consider an example, we can think that, okay, let's say, so this block, we encode this block as 0, 1, 0, 1, for example, and the next block as 1, 0, 1, 0, right? And next block probably like 0, 1, and then next block as 1, 1, 1, 1, 0, for example, right? You can see that we just connect them all together, right? And then, so yeah, those are the point of connection, okay? So it's just a simple example. Okay, next we're going to define what is uniquely decodable code, okay? So this is kind of interesting. So the uniquely decodable code is defined using the star extension code. Okay, so we do not consider the block code of length n, right? We need to consider the extension code. Okay, so NFG code is called uniquely decodable if it's C star, so which is the star extension code, is non-singular. Okay, so which means that it should be 1-to-1. Okay, so it basically means that if the star extension code is non-singular, right, then that is uniquely decodable, right? We don't need that to be prefix or whatever, right? As long as the extension code is non-singular, then it is uniquely decodable. Okay, so that's the definition. Right, next we need to take care of the prefix. Okay, so let's formally define what is a prefix, right? So prefix is nothing but if a code appears in the beginning part of another code, then basically that's a prefix code. So that is a prefix of the other code, right? So mathematically, it means that if we have x, y, two block of source symbols in x star, okay? So let's say x is a1, a2, up to am, right? And ai is in x, and y is b1, b2, up to bn, and bi is also in x, right? And then we say that x is a prefix of y if, okay, so if one is a prefix of another one, at least the first condition is that m has to be less than or equal to n, right? So if one has to be shorter or at the same length of the other one. And then second condition is that for I from 1 to m, and the ai and the bi has to be the same. Okay, then we say x is a prefix of y, right? So for example, let's say if x is 0, 0, 1 and y is 0, 0, 1, 0, right? And clearly, so so it's the prefix of y, right? So this definition basically tells you that. All right, so this is a prefix code and uniquely decodable code, right? And extension code. Okay, any questions? Okay, then let's define what is a prefix code. Okay, we say an NFG code is called prefix code. Okay, so it's called prefix code. Basically, it means that there will be no prefix. Okay, so sometimes there will be different names here. It is also called prefix-free code, to be more clear, or instantaneously decodable code. Okay, so it basically means that there's no code word, it's a prefix of another one. Okay, so if no code word is a prefix of another code word. All right, so this is called prefix code, right? So yeah, let's see one example here. A, B, and C. Let's see, A is 1, B is 0, 1, and C is 0, 0. So it is a prefix code. Why?
Because B starts with 0.
Yes.
And B has C 0.
Yeah, but B is not part of C, right? So prefix code has to be for any, wait. So there will be so this code has to be the same as the other code for the entire code. Okay, for example, so this is a prefix, X is a prefix of Y, right? So X has to be here, right? It doesn't mean it's not only they start with the same, So it has to be, if B is 0, then it's the prefix code. Sorry, it's not the prefix code. Okay, yes.
Just to be clear, the 0th element is the leftmost one. Is the first element.
Yes.
Okay.
Of course.
So we go from left to right.
Yeah, left, right, all the time. So this is a prefix code. Okay, and so what is not is this. So if we have ABC, I have 1, 1, 0, 0, 1, right? So this is not a prefix code. Right, the reason is that A is a prefix of B, right? So A is part of B, right? So in this case, we do have a problem here, right? So for example, let's say if I have a encoded code word is 110100, right? So in this case, we could have problems, right? Because the first one could be an A, right? Second one could be an A, right? And this one could be a C, right? And so on, right? Let's say it's not done yet, okay? And so we have another interpretation here. For example, this one is A, right? And 1, 0 here. This could be a B, right? And 1, 0 here. It could be a B again, right? So we have two interpretations of this. So therefore, in this case, the prefix code is not good, right? Okay, by the way, so is prefix code always bad or always not uniquely decodable? So is it possible that we have a prefix code and then we do not have any ambiguity? Is that possible? Like what?
1 and then 1 0 and then 1 0 0.
How many? Let's say how many? No. What I mean is that so in general, would there be a prefix code? We can have the uniquely decodability. Yeah, let's see. So the answer is yes.
Well, I I was gonna say like you could use a terminator. So instead of making prefix code, you can make it like a suffix code. So it's like so kind of like what Mark was saying, like A is like 0, 1, and B is 0, 0, 1, and then C is 0, 0, 0, 1. So
0, 1, 0, 0, 0, 1, 0, 1. Let's say, we'll say A is what?
0, 1. B is 0, 0, 1. C is 0, 0, 0, 1.
Yeah, but it's not. It's a prefix code, right? So none of them is a prefix of the other one.
Yeah, I guess.
Yeah. So my question is, can we have a prefix code, a non-prefix code? Okay, meaning one is a prefix of the other one, but we still can uniquely decode it. Is that possible? Yeah, think about it, right? So probably we're going to give an example later, not now. Okay, great. Yeah, it's kind of tricky. So why I want prefix code, right? So of course there's some advantage of the prefix code. Okay, so one kind of intuitive answer is that, so I have a theorem here. So the prefix code, yeah, name kind of counterintuitive, right? Prefix code means that there's no prefix, right? So none of the code word is a prefix of the other one, okay? So prefix codes are uniquely decodable. Okay. So that's why we want a prefix code. Let's prove it. Okay, how to prove it? So basically it means that if none of the code word is a prefix of the other one, of another one, then the code is uniquely decodable. Basically meaning that for all the extension codes, it's not singular. Okay, so yeah, let's do this, right? So let's see how we can prove that. So basically, we let this code be a prefix code, okay, and then we let X and Y, so they are in the extension code, okay, and so we'll assume that X and Y are equal. Okay, then we're basically to show that, okay, then we have the one-to-one mapping. Okay, so that's the definition. Let's see how we can do that. Actually, it's quite obvious to see, right? So let's see, let's assume that X is given by this. We have C1. Yeah, let me write it this way. So now basically we consider two code words, right? And we'll assume they are the same. Okay. And then the only thing we need to show is that there's only one possibility of parsing, then we're good, right? If there are two possibilities of parsing, then we're not good, right? Is that clear? Right, now we just showed there's only one parsing possibility. Okay, so let's assume that X equals to C1, C2, C3, and so on. Let's say we have Cn here, okay? And for each Ci, so that's in our code book. And Y, so we have C1 prime, C2 prime, C3 prime, and so on. We have Cn prime, and Ci is in our code prime. Okay, so now we have two parsings, right? So basically we're going to show that, so C1 and the C1 prime has to be the same, right? Is that obvious? Yeah, basically, the way we're going to see that is that, okay, what if they're not same, then what happened, right? So, okay, so basically now we can see that, so one thing is that LC1 and LC2, they have to be the same. Does that make sense? Right, if they're not the same, then one has to be a prefix of the other one, right? No, sorry, C1 prime, not C12, obviously. C1 prime. Right, so basically, what I want to say is that the length of this guy and the length of this guy has to be the same, right? So if they're not the same, then one will be a prefix of the other one. That makes sense? Right, because x, y are the same, right? So yeah, I mean, in the beginning those are the same, right? So if the lengths of C1 and C1 prime are not the same, so one will be a prefix of the other one, right? Right, okay, so let me write it down. Yeah, just let me know if you're clear about this or not, right? Otherwise I'll keep asking. So because otherwise the shorter one is a prefix of the longer one. Yes.
Okay, if like C1 was 1, for example, and C1 prime was 0, 0.
It cannot, because they're the same. Right, so x and y,
Okay.
yeah.
Okay.
Yeah. Right, then,
I get it.
yeah, so the idea is that, okay, so now, let's say we pick two code words that are the same, right, basically one code word. Want to show that the parsing has to be exactly the same. If the parsing is different, then it's not uniquely decodable, right? Okay, so that's the idea. Okay, so now, very good. Any other question? Okay, great. So by the same argument, right? If they're the same, right, we just remove those, and then we'll look at C2 and C2 prime. Okay, and by the exact same argument, right? By the similar argument, we have LC2 and LC2 prime, they are the same. Okay, and then we just continue, right? And then we can conclude that so x and y have the same parsing, right? And then we can say that hence C is uniquely decodable, right? If they have the same parsing, of course, you know, there's only one possibility for decoding, right? Okay, questions? Yes.
Yeah, so just for the example before, like ABC thing, yeah, like for the prefix code, like if we are given like 1, 0, like can we decode it, or like that case just never happens?
You mean which one? This one or this one?
Yeah, the upper one.
The upper one.
Like if we are given 1, 0, and like that's it.
No, it cannot happen.
It's not.
Yeah, 1, 0 cannot happen. 1, 0, 0 can happen, right? It's like, you know, you need to map your source information with this, right? You have A, you have this, B have this, C have this, right? Then there's no way to have a 1, 0. Okay, any other questions? Okay, great. Okay, so now let's summarize a little bit, right? So far, so now we have several cases, right? So the first one is that, so we have the set of our all codes. Okay, so they're the biggest set, right? And then we talk about, so this some code that satisfies this one-to-one mapping, right? So it's called non-singular code. Okay, but that doesn't mean that all the non-singular code is uniquely decodable, right? Because one could be a prefix of the other one, so that can make things bad. Therefore, the next, so within all the non-singular code, so we have the concept of the uniquely decodable code. Okay, and within the uniquely decodable code, so we have the concept of the prefix code. Okay, so now you may wonder, okay, so we have something here, right? So meaning that some of the non-prefix code is still uniquely decodable, right? So let's see an example. Uniquely decodable, but not prefix. Okay, so I can give you a very simple example, then you can cook up with all examples, right? For example, let's say x have only two symbols, 0 and 1, okay, or a and b, right? And then I encode x0 as 1 and 1 as 1, 0. So is this code uniquely decodable? Yeah, of course it's yes, right? So you can try it, see why. Okay, so this code is uniquely decodable. Okay, there's no ambiguity. Okay, yeah. All right, and then, yeah, let's see. Okay, so yeah, then, yeah, let's see some definitions for the average length again, and then we'll talk about the requirement for the prefix code. Okay. Yeah, again, so we use this LX or this LC to denote the length of the code word. Okay, so in the extension code for X in here, right? And then we can define our average code length, right? So again, so we use ln to denote the average code length of C here, right? So that's equals to expectation. Okay. So yeah, this is the length of the code, right? We kind of seen that before, so here is just a review. Okay, and then we say a uniquely decodable code is optimal. So if the length of it is the smallest. Okay, so we say a uniquely decodable code C is called optimal if for all other uniquely decodable code C prime, okay, for the same source. Okay, we say if ln of C has to be less than or equal to ln of C prime for all C prime, then it's optimal. Okay, so basically it's the shortest code. Okay, so next, let's take a look at the Kraft inequality. Okay, so now we just focus on the prefix code, and then we're going to see that for all kinds of uniquely decodable code, okay? So one of the reasons that we focus too much on the prefix code is that it is easy to construct. Okay, and let's see. So basically, we have a theorem. So the length function L of any prefix code F, okay, so that's from xn to y star, okay, we still consider block code here, right, and the y here, let's assume y is only in 0 and 1 for simplicity, and later on we're going to extend it. So this satisfies the following inequality. The summation of over all the possible, all the source with block length n, and then if we use 2 to the power of Lx here, so if we do this summation, so this has to be less than or equal to 1. Okay, and this is called Kraft inequality. Okay, and this is the unnecessary condition, right? If it's a prefix code, this inequality has to be satisfied. Okay, but it's also achievable. Okay, so it's sufficient and necessary. Conversely, converse given a set of integers L1, L2 until L, this guy, this is the total number of source blocks, right? Satisfying this inequality, there exists a prefix code with code words of this length. Okay, so meaning that, you know, if we give a set of this length L and satisfying this inequality, we can always find the code word. Right? Okay, so now let's see what's the meaning of this inequality, right? We see a very simple example here. Let's say we have x and we have our code. Let's say x is 1, 2, 3. We have 3 symbols. Let's see we encode first one as 1, and second one 0, 1, third one 0, 0. So this obviously this is a prefix code, right? And then let's check the inequality, right? The first one have length of 1, right? We have 2 minus 1 here, and plus the second one, so we have 2 here. And then the third one, we have still 2, length 2, right? And if you do this summation, so that equals to 1. Right? So then basically it's a sensitivity check, right? So the inequality is good. Okay, so now let's prove it. Okay, the proof is kind of very tricky, so let's see how we prove it. Okay, so basically what we do is that we need to construct a code tree representation, code tree representation. Okay, so basically we assume that the maximum code length is given by L max, right? So this is the maximum code length. So the maximum of Lx for all x in here. Okay, so this is the maximum code length, right? So basically what we can do is as follows. Let's consider another example here. So let's say we have x and we have c here. Let's say we have x is 1, 2, 3, 4, and c is 0, 1, 0, 1, 1, 0, 1, 1, 1, 1. Okay, so we want to have 3 digits here. Okay, so basically we could construct such tree. So basically we always start, you know, this is the root of the tree, and now we're going to do this, right? So let's give a rule here, right? If we go up, we mark the edge as 0. If we go down, we mark edge as 1, right? You can do reversely, it doesn't matter, right? So then we have our second layer. Okay, so basically this means our code word, right? In the first one, so we basically have 0, then we're done here. Okay, and for the second one, we have 1, 0, right? And then so we have, if we go up, we have a 0 here, right? So this is the second one. Okay, 1. So this is 0, and this is 1, 0. Okay, and for the third one, and we're done here for the second one, right? And for the third one, it's 1, 1, 0. Then basically we're going to do this again, right? So if we go down here, we have a 1, right? And then we'll have up and down, right? We'll have 1, 1, 0 and 1, 1, 1, right? This is 1, 1, 0, this is 1, 1, 1. Okay, so this is our code tree. Right, that clear? Okay, very good. And given this code tree, basically we can do some very interesting things here. Okay, the first of all, we can see the length of the code tree is what? Oh, cannot see it. Interesting. So we need to go up a little bit. Can I add it? Oh, great. Yeah, good enough. Okay, so the length of the tree is what? Or the L max of the tree is 3, right? Okay, very good. And then basically what we're going to do is as follows. So we're going to extend this tree to another code. Okay, let's see how we extend it. So basically what we're going to do is that we're going to fill everything missed here, right? For example, so the length of the tree is 3, right? So basically we're going to fill up it. Let's see. Yes. Okay, so yeah, it's kind of awkward. Here I have 2 more. You know what I'm doing, right? So here I can fill up this tree. Okay, very good. And by filling up this tree, so by the same rule here, we can have a new code. Okay, the new code is called C tilde. Okay, right? And then let's see what we are doing here, right? So the basically the key part here is that so we can count all the leaves here. Okay. So yeah, let's write it. So basically the first step is that we're extending the code tree to another code tree. Of das L max. Okay, and the benefit of doing this is that now the tree is kind of full, right? And for this, so we can easily characterize the number of leaves here. Okay, so basically, now let's denote the set of all the leaves, the set of each leaves of each code as you see here. Okay, so basically, so UC basically means the set of leaves of code in C tilde that are children of the code word C. That makes sense, right? So for example, so let's say if let's say U0, okay, and then this basically means this leaf and this leaf, and U10 means this leaf and this leaf. That makes sense? Okay, so that's basically what we mean. Yeah, let's write it down. For any code word in C, we let UC be the set of leaves of C tilde which are children of C. Okay, so that's the definition of UC, right? So now we can count the number of UC here, right? So we can characterize the cardinality of UC. So what is that? Right, so basically this gives you this. So this number equals to 2 power of L max minus LC. Right, let's see whether it makes sense or not. For example, for the first one, right, so basically what we're going to have is that, so this is, let's say, I choose another color here. So this is 2 to the power of 3, right, minus the length of UC, length of C, right? The length of C here is 1, right? 3 minus 1. Oh yeah, so yeah, that's right. So that's equal to 4, right? So basically, the children of this guy is 1, 2, 3, 4, right? And similarly, for the second one, so it's 2 power of 3 minus 2, right? Because the code length is 1, 0, right? So that equals to 2, and then here is 2, right? And for the third one, right, it's 2 power of 3 minus 3, so that's basically 1. So yeah, that's basically 1, right? So basically, so then we can have this relation, right? Therefore, so this 2, so this can give you the total number, the cardinality of UC. Okay, all right, good. All right, and given this, then, so we have another important condition, right? So we know all the UCs are disjoint, right? Because of this construction, so all the UCs are disjoint, right? So this is U1, so this is U, so this is U0, and this is U10, and this is UC of 110, and this is UC of 111, right? They're all disjoint by this construction, right? Therefore, we can conclude that since the UC are disjoint, right, then we can see that the union of UC, okay, would be definitely in our extension code. Okay, right? Because of this, then we can conclude that, so then the sum of, let's see, over all the code word in C, and then we sum the cardinality of UC. Okay, so I mean, because of this and this, so we can conclude that so this is upper bounded by the cardinality of the of this code, this tilde, right? So without a disjoint condition, we cannot say that, right? Okay, very good. And then from here we can get that. So just use this relationship, right? So the first one is that C equals in C, then we have 2 power L max minus LC, right? And then so we know the cardinality of this guy, right? Because that equals to number of leaves, right? So that's because so that will be less than or equal to L max, right? And now we have L max here and L max here, so this can be cancelled, right? And then we can conclude that so this guy will be less than or equal to 1. Okay, so this is the first part, right? We show, so this has to be true, right? And then the second part, so this is basically to show the first part of the theorem, right? So this has to be true, right? What about the converse? So what is the, yes, not converse. So this is basic the impossibility, right? So we show this has to be true, okay? And what about the sufficient condition? Okay, so it basically means that we need a construction. How to construct the code? So we know the inequality has to be true. So how to construct the code? Okay, we're done. Yeah, but I want to talk to finish the construction. Will that be possible within like 2 seconds? Yeah, this is the construction, right? So here we can see if we can just follow this step to construct the code, that's it, right? So this is the construction. Okay, that's it, right? So basically, so this use the code tree to construct it, and then we're done. Okay, great. So next class we're going to talk about what is the, well, we're going to talk about the same thing for the uniquely decodable code. Okay, thank you.